Hello, good morning everyone. So Dr. Bennett here. In this video we're going to have a look at deriving and analysing the Breguet range equation specifically for a piston propeller driven airplane. So I very much recommend that if you haven't done so already, go back and watch the previous video where we looked at the Breguet endurance equation for piston propeller driven airplanes. We're going to use a lot of the same techniques to derive this Breguet equation as we did in the previous video. So this one should be a little bit shorter. It's a little bit more of a simple equation, but we're going to use a lot of the same techniques. So as before, we're going to start with the so-called average value method for range, which states that the range of the airplane, so the distance that we can travel on a given fuel load, is equal to just simply our airspeed multiplied by the endurance. So let's say, for example, we have endurance given in units of hours, and our airspeed is given in miles per hour, for example, then the units of this equation becomes miles per hour multiplied by hours to give us a range in units of miles, distance, right? So that makes sense. So this is the average value method equation, and in the previous video we did a little bit of work on our endurance equation. So we said that endurance was equal to the amount of fuel that we have to burn, this is our fuel load, delta WF, divided by the rate at which we're burning it. So this dot notation again is just shorthand for a derivative with respect to time. So this is how much fuel per unit time we're burning through. So our range equation just becomes our airspeed multiplied by this ratio. So we simplified this in the previous video using this equation. This is our rate of fuel burn. It's a function of the brake specific fuel consumption of our piston engine. C is the notation for that. Divided by the propeller efficiency factor. This is a number between 0 and 1 describing how well our propeller converts power from the engine into thrust via the propeller, multiplied by the average power required to overcome the drag. So that can be replaced into here, V airspeed delta WF over C over eta prop, in the denominator average power required. And if power is force multiplied by velocity, our force in this case is drag, because this is the power required to overcome the drag. So PR average is just force times velocity. Our force is drag average multiplied by V. So this V here is going to cancel with that V there, and that's going to leave us with this equation, C over eta prop, in the denominator D average. So this is our average value method equation, and that's our starting point for the derivation of the Breguet equation. So let me transfer that back up to here for our derivation. So as before with the endurance equation, we're going to say that range is equal to an integral between two specific weight stations. W1 is our starting weight of the airplane, W2 is our ending weight of the airplane. So that describes the amount of fuel that we have to burn. Because W2 is always less than W1, because we're burning fuel, we need a negative sign out the front. And then that integral basically replaces the numerator in this equation. So C over eta prop, so 1 over C over eta prop D integrated with respect to W. Okay. So that gets us started, and if we just perform this integral now, that should lead us directly to the Breguet range equation, specifically for a piston propeller driven airplane. So our little trick that we used in the previous video to get us started was to essentially multiply this term by 1 in disguise. So if lift is equal to weight in our cruise problem, so remember this means that essentially we're flying at constant altitude. If lift is exactly equal to weight, we will continue at the same altitude, right? Therefore, L over W is equal to 1. So we're going to multiply this term by 1 in disguise. 2 prop over C. Then I'm going to do L over D 1 over W D W. So I've grouped these things together because what I'm going to do now is take out everything from the inside of the integral to the outside that doesn't depend on W. So out the front now I will have eta prop over C. Again, converting these magnitudes into coefficient form just so that the equation is a little bit more generic. And then I've just got the integral of 1 over W with respect to W. So pretty straightforward, right? Let's go back up to here. I can integrate this directly now, so eta prop over C, CL over C, D, pen's running out a little bit, and the integral of W, 1 over W with respect to W is the natural log of W evaluated between our two weight stations. So yeah, let's just tidy this up real quick. But this is essentially the Breguet range equation for a piston propeller driven airplane. Natural log W2 minus natural log W1. And then the final little bit of tidying up to do, I can push the negative sign into this bracketed term on the end, so I can just flip it around, W1 minus log W2, and then finally, using the law of natural logarithms, I can do that, right? So yeah, this is the Breguet range equation specifically for a piston propeller driven airplane. So let's just have a quick look at this equation. If we want to maximize range, we need to maximize our propeller efficiency factor. So remember, this is a number between 0 and 1, hopefully closer to 1 than 0, right? Describing how good our propeller is at converting power from the piston engine into thrust. So a good number for that is probably somewhere in the order of maybe 0.7 to 0.85, something like that. So we need to maximize our propeller efficiency factor for maximum range. We also need to minimize, because it's in the denominator, the brake specific fuel consumption. So that seems intuitive, right? Minimizing our fuel consumption is going to maximize range. We need to maximize our fuel load, obviously. The more fuel we have to burn, the more range we're going to get. So if we maximize our fuel load, that's going to maximize this term. And then finally, we are going to be maximizing our lift to drag ratio directly. So it can be shown, and maybe we'll do this in another video, that our total drag, so total drag or thrust required, the two things are the same because we're using thrust to overcome drag, plotted against airspeed v, the total drag curve looks like a parabola like that. And if we separate the two components of drag into parasite drag and induced drag, one of these is a function of v squared, one of them is a function of 1 over v squared. As I said, probably we'll do this in another video. But essentially, to maximize our lift to drag ratio, because we are flying with a constant lift, is equivalent to just simply minimizing drag because it's in the denominator. And our minimum total drag point occurs at the point where the parasite drag and the induced drag are equal to each other. So our parasite drag coefficient, CD0, should be equal to our induced drag, KCl squared, in order to maximize our lift to drag ratio in this term. So that is it. That's the Breguet range equation specifically for a piston propeller driven airplane. Stay tuned for the jet power equations coming up in the next videos. Thanks.